Thanks so much. So, okay, so I'm happy to introduce the second speaker of the session, Volker Schlue from University of Melbourne, who will now tell us about cosmology, expanding black hole cosmologies.
Yeah, thank you so much for inviting me to this conference. I realized from the first talk it's actually really great to attend some talks again, and I'm actually really happy to see lots of you, even if it's just through a small window. So yeah, thanks to the organizers, and specifically thanks to Sangjin for the invitation to speak in this session. Okay, so I want to begin this talk by talking about de Sitter. So this is going to be a talk in general relativity, and what most people, or maybe the spacetime that people are most familiar with is simply Minkowski spacetime. But here, the main player is de Sitter spacetime, and it plays the role of, you can think of this as the analog of Minkowski space in the setting of a positive cosmological constant. So you see de Sitter space is sort of the simplest solution to the Einstein equations with a positive cosmological constant. And it can be realized as a hyperboloid in 5-dimensional Minkowski spacetime. So think of take Minkowski spacetimes in 4+1 dimensions and consider the time-like hyperboloid, and take as its metric the metric induced by the ambient Minkowski spacetime, and that's de Sitter. And it has very different topology than Minkowski space. The topology is it's S3 cross R. So the spatial sections are closed, and you see as time goes on, which is the arrow pointing upwards here, those spheres, these S3s, these 3-dimensional spheres, are expanding. So as such, it's the simplest and first model of a closed expanding universe. And as you now know, that many of you will know that general relativity can be formulated as an evolution problem, and you could immediately in this setting ask the question, well, okay, let's say I view one of those spatial slices S3 as my initial data, and I perturb the geometry of that 3-dimensional sphere ever so slightly, then what happens in evolution? And Friedrich showed in the late 80s that the resulting spacetimes are future geodesically complete. So sometimes this is referred to as the stability of de Sitter, but I want to point out that this is actually a little bit different from, let's say, the stability of Minkowski spacetime, because it's not true that the spacetime after a very long time converges globally back to de Sitter space. In Minkowski space, in all directions, eventually the metric will go back to Minkowski space, and it will be so globally. In here, this is not the case. So globally, the spacetime will not converge back to de Sitter, and that's the first indication of the asymptotic degrees of freedom that will play a role in what I'm talking about. So I will say a little bit more about de Sitter, because these pictures will come up all the time. So I introduced here de Sitter as the hyperboloid, as a time-like hyperboloid in 5-dimensional space. And another depiction, which you also see frequently, is that as a Penrose diagram, which you see here in the top right corner. And the way the two things are related is you view de Sitter space as a spherically symmetric space with respect to a chosen time-like geodesic. So here, let's say you intersect this hyperboloid with the plane that runs through the central axis, and then you get this curve, which is a time-like geodesics, and now you view the space-time as spherically symmetric with respect to this observer here. And that means that you are foliating this S3, which sits here by S2s, which have a radius which is first 0, then increase and reach a maximum value, and then decrease again to 0, and you end up on the antipodal line to this observer, which is here. And by doing that now, you know, conformal infinity, which you used to be, or which is sort of here, this is the S3 at infinity, because you've now removed 2 points, this becomes a cylinder, which is future null infinity. Now, another, another big difference to Minkowski space that you should keep in mind is that if you consider the past of any observer, the past is not the whole space-time. So in Minkowski space, no matter what time-like geodesic you take, and with whatever straight line you take, the past of that curve is always the whole space. Here, that's not the case. So this diamond-shaped region that you see here is the intersection of the past with the future of gamma. And the reason that you see immediately it is like this is because I told you that the metric on de Sitter is induced by the ambient space. So to look at, say, the past, I just have to take a point and look at the past cone in Minkowski space and intersect that cone with the hyperboloid, and that tells me what the past is, and this is how you get these diamond-shaped regions. You see here in the same picture in the Penrose diagram, and the Penrose diagram is so useful because it preserves these causal relationships where you see them very easily. But in particular, what you get if the past of the observer is not the whole space-time, well, then it has a future boundary, and that future boundary is the cosmological horizon. So that has the physical meaning. If you have some other observer which crosses that cosmological horizon, then that observer will not be able anymore to communicate with gamma. So in de Sitter, every observer has their own cosmological horizon, right? There's nothing special about this one. Every observer has their own cosmological horizon. Now, moreover, I want to emphasize that even though the whole spacetime is expanding, if you just look at the coordinate patch that's given by the past of this observer, in that domain, one can actually find a coordinate system so that the metric looks static, it looks time independent, and that's going to be relevant for what I say in just a second. So, okay, I've talked a little bit about the geometry of de Sitter, and I've outlined a little bit how the geometry of de Sitter is very different from Minkowski space. But when you are thinking about the evolution problem in general relativity, it is often quite useful to gain some intuition by just looking at the wave equation. And the first thing that I want to say, if you look at the wave equation on de Sitter, solutions do not decay. So you can see that, for example, from a result of Vagi from 2008, which tells us that general solutions of the wave equation on de Sitter have this form. So that means, so T here is the ambient time in Minkowski space, and V0 and V1 and V2, they're free functions on the sphere at infinity. So one way of saying that is that given any smooth functions V0 and V1, V2, I can find a solution to the wave equation which looks like this. In particular, as T goes to infinity, I'm just left with V0, and V0 is some free function, right? Which is not zero. So this is quite different from a Minkowski space, and it's the first indication of asymptotic degrees of freedom. But nonetheless, of course, what you have heard, what many of you might have heard, is that, well, but in de Sitter I have very strong decay. I have, in fact, exponential decay. And the way that is reconciled in this picture is that as I said, there's nothing special about this observer. Choose any point and look at some time like geodesic that ends in the point Q. If you look at the past of this, indeed that region is static, and there's a static time which is related to the ambient time exponentially. And so what you get in the past of any point is exponential decay, but to a constant. The point is simply that this constant is potentially different at any point on the sphere at S3, and it is and thus it's a functional degree of freedom even for the wave equation. You see the same story unfold if you look at the Einstein equation in the context of Friedrich's proof. So the way he solved this problem was by what is now called the conformal method. You pass from the physical metric to a conformally changed metric, and by doing that, he managed to reduce this global existence problem to a local existence problem. And you, similar to here, you have a notion of data at this conformal boundary at infinity. And now it turns out that, of course, for the Einstein equation, not like for the wave equation, there are constraints. But he, on the data, and when he discovered that the constrained equations on this conformal boundary take a very simple form. They look like Maxwell's equations. They just become a simple equation for the rescaled Weyl curvature, for the electric part of the rescaled Weyl curvature. So, okay, it's an equation, but apart from that, it's free, right? This is the sense in which the spacetime does not converge back to de Sitter. You have, in particular, here a free induced conformal metric on the sphere at infinity, which need not be the standard metric on S3. Okay. But now I want to talk about not de Sitter, but Schwarzschild de Sitter. And the way you can think of it is, if you remember this Penrose diagram here of de Sitter, and let's just take the upper part of it, then I can think of Schwarzschild de Sitter as arising from de Sitter by replacing these two antipodal observers by black holes. And then you introduce two new horizons, the event horizons of the black holes, which means that the resulting spacetime is not geodesically complete. It is now possible for an observer to cross the event horizon, which will make it impossible for him to send a signal to infinity. But the same way that an observer had its cosmological horizon, also the black hole has its cosmological horizon, which is the future boundary of its past. And as before, the past of the black hole is not the whole space. So you what you have here. So the complement of that, if you want, is what are called the cosmological regions, and the cosmological region, and I'll say more about that, of course, in a moment. But what I want to highlight is, at least say for Schwarzschild de Sitter, is that the past of the black holes is a static region, the same way that we've seen analogous to the static patch in de Sitter. And in some sense, the larger topic of this talk here is the stability problem of Schwarzschild de Sitter. So the question is, you have some now. You start with data corresponding to the induced metric of the Schwarzschild de Sitter solution. You perturb it ever so slightly, and you ask what the maximal development look like. So are these regions, these static regions, stable? As in de Sitter, the cosmological regions futuristically complete? And what does the asymptotic geometry look like? Now, many of you will know that a big part of this problem has been solved by Hinz and Vargy in 2017. Who showed that these static part of the black hole exterior, the domain between the two horizons, between the event horizon and cosmological horizons, is stable in the strong sense that here the solutions converge exponentially fast to a member of the Kerr de Sitter family. So the Kerr de Sitter family is non-spherical, not spherically symmetric. They as opposed to Schwarzschild solution, they have a small angular momentum. But the point here is that as you are approaching this point here, the solution, they establish that the solutions decay exponentially fast to a certain member of this Kerr de Sitter family. And I'll say a little bit more about this proof, or I want to highlight two things about this proof. One is, as opposed to relate to the earlier discussion, one of the things I want to highlight is that here, in the same way that, say, solutions to the wave equation and the static equation converge to a constant, here, if you want to think of that constant as an explicitly known family of solutions, right? The asymptotic state here is known. It's a question of identifying it. And the way that they solve this problem is in generalized harmonic gauge. So you look at the Einstein, you look at the you use a gauge where the Einstein equations are viewed as quasi-linear wave equations for the metric components, and what they do is both the specific of the gauge and the asymptotic state, they depend on the solution itself, and they are found iteratively. So this relies on looking at the linearized equation and proving a resonance expansion for the linearized for the solutions of linearized equations, which means that you prove that the solutions to linearized equations are exponentially decaying up to a finite number of terms, which are potentially exponentially growing. But then what they managed to do is to relate those exponentially growing modes to pure gauge solutions. And this way, by eliminating these modes step by step, you find both the final gauge and the final state. This result also applies to the static patch of de Sitter. So you can also prove that the static patch of de Sitter is stable in that sense. And so if you ask, okay, but what does it now mean for the stability of the expanding region? Well, if you think, for example, in the same way that I talked about earlier, looking at the wave equation on de Sitter, take a point in the future, take a point at future null infinity and consider its past. Well, then if you're just looking at the past of a point, that's essentially a perturbation of de Sitter. So you could apply the result here to obtain exponential decay to de Sitter in a specific gauge. But this gauge is like the constant. Once you're moving away from it, it becomes a full gravitational degree of freedom. So here you would get the stability of the past of a point. You could also ask, what would you get from Friedrich's result? You could get a little bit more if you look at a space-like surface here, which stays away from the stays far away from the event horizons. Also, this is I will not explain exactly how, but this can also be viewed as a perturbation of de Sitter, and then you can apply his result to conclude that the two solutions agree in the domain of dependence, and from that you would get the stability of such a region which now intersects future null infinity in something bigger than a point, namely a whole set. But what you cannot do with these results is you will not be able to get close to these points where in the Penrose diagram the event horizon and the cosmological horizons intersect, and in some sense this is the main problem. Now, so what I am doing is I'm considering the characteristic initial value problem, and I look at data which is exponentially fast decaying to a member of Kerr de Sitter. This is justified by the result of Hind's inversion. In other words, I use their result as an input for my data. Now, but in view of what I've said, you don't know what the asymptotic geometry, what the asymptotic geometry looks like. So now you, in some sense, you're trying to solve a global existence problem, but you don't know what the asymptotic state is. So you ask, well, how can you do this? The first step that you have to do and that I did is to identify a quantity that decays no matter what the asymptotic state here is. And that turns out to be the conformal vowel curvature. So let me say a couple of words about the conformal vowel curvature. In the same way that Minkowski space is well, the space that is flat for which the Riemann curvature vanishes at every point, you can view as de Sitter as the space which is conformally flat. And one way to see this is maybe by something that you could call the hyperbolic analog of the stereographic projection. So you pick a point here and you project the hyperboloid on a plane, which is a copy of Minkowski space, and you find that the two metrics are conformal to each other, and that immediately implies the Weyl curvature vanishes. Now, for Weyl curvature and Riemann curvature, and for lambda equals 0 is the same, but for lambda equals positive, these are different. These are different objects. Now, okay, you have now a quantity which is 0. How can you, why should you expect that this quantity decays in general? Is if you look, for example, at Schwarzschild de Sitter, you could find that just one component of the Weyl curvature is non-vanishing, and that expression here maybe looks, very familiar from the only non-vanishing component of the Riemann curvature for Schwarzschild, but it has a different meaning now, because I claim that an expression like this means that this quantity in fact decays in time. And the reason this is so is if I want to look a little bit more at the geometry of the expanding region, you have here in Schwarzschild de Sitter is spherically symmetric. We look at the Penrose diagram, every point corresponds to a sphere. And now it turns out that in this expanding region, and this is the reason it's called the expanding region, the spheres are increasing towards the future. In other words, I can view the radius itself as a time function. And the level sets of this time function are space-like hypersurfaces. So in this region here, the radius is like time. So, okay, now this is all very good, but how are you gonna implement this in for a general dynamical space-time? And that's where the double null gauge comes in so naturally, because what one can do is, okay, I have here my characteristic agenda value problem, and I look at the spheres that foliate the cosmological horizon, and I can choose a function such that the level sets of these functions are my spheres in the cosmological horizon, and then I extend that function to the whole domain by solving the iconal equation. And I want to do that in such a way that if I construct the null hypersurfaces starting from these spheres and construct null hypersurface by solving the iconal equation this way, I want the intersection of these null hypersurfaces to be always spheres. In other words, topologically spheres, and then I can define a function, a time function, to be simply the area radius of those spheres. And I hope to do that in such a way that future null infinity, the conformal boundary, can indeed be identified with all spheres of infinite radius. Now, it turns out that to do that, that is actually a big part of the problem, and there are a lot of things to be understood how to do this. But in a first step, you can let us assume that you have done this. You have a general now space-time which can be foliated in this way, and you then if you do that, then you can prove the following. You can, if you are now given a domain, which you think of as the expanding region lying to the future of the cosmological horizons, and you assume that this region can be expressed globally in double null gauge, and with respect to that double null gauge, you make certain assumptions on the Christoffel symbols and their derivatives. And the statement is that in such a region, I can prove that the Weyl curvature decays at exactly the rate that we've seen earlier for, say, Schwarzschild de Sitter. now you should think one. If I know, of course, the Christopherson and the derivatives, and then I could, in principle, compute the curvature. But the point is that this is the result of an energy estimate that captures which is much better than what you could obtain in this way. It's the result of an energy estimate that captures the expansion of the space-time, which is manifested in this global redshift effect. So let me just say very briefly what I'm doing here, as I'm not working in a generalized harmonic gauge. I'm working on a framework that is much closer to the original proof of the stability of Minkowski space. So what you're doing here is you're not looking at the equation satisfied by the metric, but more by the curvature. And the idea is that these equations look like Maxwell's equations. And Maxwell's equations are Lagrangian theory. So for Lagrangian theory, you have an energy momentum tensor, and with that you can construct currents, and from that conservation laws. So the analogous thing here is that you have for these equations, you have a so-called Bell-Robinson equation, Bell-Robinson tensor, which allows you to construct currents, and from that conservation laws. Much in the same way that you would prove these energy identities for, let's say, the wave equation or the Maxwell equation. And this is exactly why I knew what to do, because I had to study the wave equation first. But I just want to say briefly what happens is you have now, because you have a double null foliation, you have this area radius, of which you know that the level sets are space-like. You can now prove an energy identity between two of these hypersurfaces with respect to a certain time-like vector field, which I'll call the global redshift vector field, because it has the property that for any solutions to this equation, you obtain a positive current. The divergence is not just positive, but in fact it bounds the energy from below with a certain vector, and that gives rise to that the vowel curvature in L2 decays. Now this is weaker than what I've stated. To obtain, I stated that the vowel curvature, if you want, restricted to those spheres, it decays at a certain rate. And so to obtain this via Sobolev inequality, you also need that all the tangential derivatives on those surfaces decay at a certain rate. Now, you could, when you say, okay, if I want to get all the tangential derivatives, why not commute with all the tangential vector fields? But as I said, these spacetimes cannot be assumed to have any asymptotic symmetry. So there is no reason that commuting with these tangential vector fields would work, because they're not generating symmetries. So the way that I go is you also find the manifestation of the global redshift vector field at the level of the commutation, and this is much harder because it turns out to one has to fine-tune this vector field and the rescaling quite carefully in order to obtain that also the commuted equation exhibit a positivity property. The problem is that if you commute the equations, there are lots of terms on the right-hand side, and now it's not enough to treat them as an error. You have to find a sign, and that's why this is a complicated story. But nonetheless, as a result of the expansion, you can find that also here you find a positive current. And then using the electromagnetic decomposition, you can find that all the tangential derivatives are. So here you control the normal derivative, and then through the electromagnetic decomposition, you find that all the tangential derivatives are controlled. So
Volker,
one thing I want to, yeah.
There's a question in the chat about the last theorem.
Could you tell me? I don't know how to pull up the chat here. Sorry.
The question is, does this mean or imply energy of linear waves is monotone?
Yes. So that's right. So and here you are. I'm proving. You should think of this as. That's right. So it's not just that an energy is monotone, but that a certain weighted energy is monotone, and because you have that weight so because you have those weights, you can see here this omega in fact scales like R. So you obtain that a weighted energy is monotone, and then as a result you get these factors in R that show you that what is at the level of the energy in fact decays. Yeah, so one thing that I do want to emphasize is that that, you know, something that you might have heard from the asymptotically flat setting, namely peeling, doesn't have, you know, there's no indication of that here. All the Weyl curvature components are on the same footing, and that has an interesting consequence, because if you look at these level sets of the radios, you could ask whether these surfaces are conformally flat, and you know the conformal flatness of the three-dimensional Riemannian manifold is related to the vanishing of this Bach tensor, and it turns out that this Bach tensor in general is related through these Maxwell equations to the magnetic part of the Weyl curvature. And if that doesn't decay at a certain, if that decays only at a certain rate, then you, in other words, if it's, I mean, in particular, if it's supported, if it's not vanishing, then you will find that these surfaces and also future null infinity will not be conformally flat. And that might have a number of interesting consequences, because if future null infinity is not conformally flat, there are a number of challenges how to define asymptotic quantities, as was already observed by Ashtekar. Okay, so I don't want to go into too much, but essentially, so this theorem has a number of assumptions, and those assumptions, as I tried to explain, they in particular capture that the spheres that I'm looking at, they're expanding towards the future, and also they exhaust this this expanding region, which is captured by assumptions of this type. Now, the broader picture here is that what I've shown you is, okay, I've made certain assumptions on the Christoffel symbols and its derivatives, and now I've tried to explain that via the Bianchi equations and energy estimates you obtain a certain bound on the Weyl curvature. But now the second part of the story is that if you now know that the Weyl curvature decays, together with certain assumptions on the data, you want to show that these assumptions that you made initially were realistic and you can recover them. And that part that part of the story turns out to be equally challenging, if not more. And I want to, when I first started working on this, I found that there are a couple of striking obstructions which really have nothing to do with the specific decay of the Weyl curvature. They already occur when the Weyl curvature vanishes identically, namely on the de Sitter space. So what I want to point out, so remember I'm solving a characteristic initial value problem. So I have initial data on these cosmological horizons. I've prescribed certain spheres, and now I want to. You could say, well, from this initial data, I now want to construct globally these double null foliations. Well, it turns out that if you perturb ever so slightly from the spherically symmetric picture. So I'm now saying, so, you know, forget about the decay of the Weyl curvature, set the Weyl curvature equal to 0, then you're in de Sitter. Look at the spherically symmetric foliation, a double null foliation in the expanding region, and perturb the spheres on the cosmological horizon ever so slightly, solve the iconal equation globally and see what you get. Well, then you find that in what looks like generic behavior, you will obtain spheres which do not correctly parameterize null infinity. They will pinch off. So they will, if you perturb them ever so slightly, they're far later in the space-time, they will intersect in spheres which run off to infinity first at certain points and then disappear in these annular regions. And you could you know, and what that shows is that, well, it's not going to be, you cannot just prescribe the whole gauge initially. In some sense, you know, that was expected from what I said earlier, but on the other hand, and that's also something we've heard very briefly in Juhi's talk before, the expansion generally helps. So it could have been expected that also here, or not expected, but one could have maybe thought that also here the expansion helps. You don't have to worry about this final gauge problem. But it turns out that here the expansion works against you. Small deformation initially is sort of exasperated over time by the expansion of the spacetime, and you end up with drastically deformed spheres. The way one sees this is actually a very explicit.
There was a quick question.
Yeah. Yeah.
About the last slide.
Yeah.
The question was, are these canonical solutions here?
Are these canonical solutions? So I will tell you what these solutions are. They are just, you know, I wanted to be sure that this really occurs. So I'm constructing them explicitly. Yeah, explicit global solutions. Let me quickly say how you do this. So, okay, you have here the picture in the Penrose diagram. You have here the red lines are my, if you want, the null lines, which correspond to the spherically symmetric double null foliation, and this is a sphere. Now, this spherically symmetric picture is not too useful to understand solutions which are not spherically symmetric, but it's really what I'm doing here is you remember that, okay, de Sitter is really can be depicted as this hyperboloid in a higher dimensional Minkowski space, and then you can think about, well, what does the spherically symmetric double null foliation correspond to? Well, it corresponds to picking points on these antipodal geodesics, looking at the cones in the ambient space, and intersecting these in this picture, and then you get these null hypersurfaces. And now you can quite easily move out of the spherically symmetric picture, because in this left picture you have a lot more freedom. I can move, you know, I can move the base point of this cone away from the antipodal line, and then what I find is that if you do that, the intersection with the cosmological horizon is a small ellipsoidal deformation, which can be as small as this displacement if you want. But no matter how small this displacement is, if you follow what the sphere does at infinity, actually in the special case, you can just find that this sphere at infinity can be written as a graph. And then as you are moving this sphere to infinity, which corresponds to letting this epsilon go to 0, you see explicitly that first one point runs off to infinity, and then it disappears in annular regions. So this corresponds to very small deformations on the initial data, which has drastic effects at null infinity. And yeah, I expect that to be the generic behavior. Now, okay, at this point you ask, okay, well, but how, are there any solutions, global solutions, which are well behaved? And what I'm going to do is show you, well, yes, there are, and I'm going to show you how to do that. And the way this is resolved is relevant to the full problem. So what I do here is, let's say you fix now two null hypersurfaces. The idea is, instead of prescribing the spheres on the cosmological horizon, let's fix it on that final null hypersurface. And then I want to solve the iconal equation backwards and construct those spheres and see how they are related to the choice of spheres finally. So the statement is informally speaking, that it is possible to choose families of spheres, an open set of data, which correspond to the choice of those spheres on these null hypersurfaces, so that if you solve the iconal equation backwards and you look at the spheres, these spheres are all conformal to the to the round sphere, and not just conformal, they are uniformly conformal, by which I mean that the conformal factor is uniformly controlled. Now, okay, in this picture here, you know, remember, I'm really just, so this is in some sense a pure gauge question in de Sitter. And I'm looking here at you know, spheres which are sections of cones in de Sitter, but therefore also, you know, sections of hypersurfaces in Minkowski space. And so it is immediate, you know, that these spheres will be conformal to the round sphere. But in general, the way that you would obtain that a sphere is conformal to the round sphere is by applying the uniformization theorem. And the uniformization theorem relies on bounds on the Gauss curvature. So I was quite surprised that if you just start from this point of view, even in de Sitter, you are quite naturally led to the so-called mass aspect function, which you should think of a quantity that is related to the Gauss curvature, but it satisfies a better propagation equation, and in particular, it turns out that the decay properties of this mass aspect function, which is here, you know, different from the case in the asymptotically flat setting by this term, is that the decay properties of this mass aspect function are related to good foliations. And you will say, okay, mass aspect function, you're talking about de Sitter, so there is no mass. So, and indeed, that is what happens for all the spheres that you are looking at here. If you compute the integral of the mass aspect function of those spheres, is always vanishing. These spheres indeed have no mass. But it was incredibly useful for me to discuss this problem in the setting of de Sitter, because here, you know, everything you do is pure gauge. There are no gravitational degrees of freedom. There's no mass. There's, you know, and it will be important to understand what is pure gauge in the solution and what is true gravitational degree of freedom. So then, give a more precise version of this theorem. It simply says that, well, if you choose the spheres at infinity, so that essentially these spheres are pretty close to being level sets of the mass aspect function. So if you look at the mass aspect function minus its average, if that decays suitably fast, that corresponds to a choice of spheres. If you then construct a double null foliation backwards and you look at those spheres, then the conformal factor is uniformly controlled. And moreover, you can show that all the assumptions that I made for the Weyl curvature theorem are satisfied. So that shows that, yes, there are non-trivial double null foliations which satisfy all these assumptions, right? Okay, but this is a pure gauge question in de Sitter. Let me just say what this corresponds to, so that if you arranged the spheres to have this property, for example, you could arrange this by choosing them to be level sets of the mass aspect function. So let me just say what this corresponds to. If you, for example, choose a gauge so that the mass aspect function, in fact, what I'm using here is a modified mass aspect function, but let me not go into that. If you're using, if you're prescribing the spheres so that they are level sets of the mass aspect function, that the mass on the sphere, the mass aspect function equals its average, then what that equation means, it becomes an equation of motion for surfaces on this last null hypersurface, which is sort of this form. You have, you should think that it's an equation for the lapse, for the separation of those spheres within the null hypersurface. The right-hand side can be computed from the slice itself, and so you get an equation of motion. So if you choose one sphere, you solve this equation of motion. Then you satisfy this assumption on the mass aspect function, and then if you use those spheres to solve backwards, then you get a globally well-behaved double null foliation. Okay, now this is of course, as I said, this is only the problem in de Sitter. So if you, for the full problem now, let me remind you, so we are looking, in general, I'm looking at the characteristic initial value problem. You have data which is corresponds to exponentially decaying energy flux along the cosmological horizon. One could, in principle, assume the same on the other surface, but there is sort of a physically relevant initial data condition on that side, which corresponds to the no incoming radiation condition. So you don't want to have additional radiation coming in from this side to study what would correspond to an isolated gravitational system. Now you have constructed those surfaces corresponding to the level sets of R. We know that in general, these spheres will start to pinch off. So you will stop the evolution and then you will choose new spheres. Now, what is quite different to, and we know that we have to do that in such a way that there's sufficient control on the mass aspect function. Now, unlike, so let's say, in the stability of Minkowski space, it's not enough to refoliate the spheres within such a space-like surface, because remember, we want to change the hypersurface. The hypersurface has the property that it pinches off to null infinity. So the whole hypersurface has to be changed. So you have to find spheres which are nearby in the space-time to the surface that you're looking at. And that is starting to look, it is starting to be reminiscent of the story that we hear from Kleinerman Schiftel about perturbations in Kerr, where you have to construct certain spheres which satisfy good properties in the neighborhood in the space-time. Anyway, the goal here is that you will eventually prove in that in the context of that larger bootstrap argument that you obtain a gauge which has the property which correctly parameterizes future null infinity. Future null infinity should be a surface consisting of all spheres of infinite radius, and it remains to be seen how this is accomplished and what the relation between the spheres initially and finally is. So I think I will stop here.